Welcome to Study Loop.
This is problem 32 of chapter 23. For this problem, we're asked to explain the resolution limit. So where does that come from? Well, first, let's look at the equation for Airy's disk. So that formula says sine of theta is equal to 1.22 lambda over d. So this equation describes a first order diffraction minimum going through an aperture with a diameter d. So if we have some diameter d here, and there's let's pretend light is going through this hole. And then we have a screen here. So let's try to draw this as a projection. So here is the screen, and light is coming through here. What you would observe is a spot here in the middle. Let's go ahead and fill it in. So we would see this spot here in the middle, and then bands around. We would see bands around this first bright spot here. And these secondary bands, they're much less bright than the first. So the angle formed from the center of this hole to the center of this pattern here, it's going to be marked here with this green line, and then we're going to also draw another line to that diffraction minimum. This angle is theta. So depending on the wavelength and the aperture diameter, we're going to get this angle theta for this pinhole here. This central region is more intense than the outer bands here. So if we were to plot this, if we were to look at this in terms of intensity, we would draw something like this. There would be the most intense region here in the center, something like that, and then a minimum, and then the secondary bands out here. So we would have secondary bands, tertiary bands, and these would be very thin and not as intense as that initial band. So this is what an object would look. This would be the pattern that we would see. Okay, so for the resolution limit, this angle is going to get even smaller. And remember, for small angle approximations, sine of theta is approximately equal to theta. So the equation for that Rayleigh criteria, it is theta res, and this is going to be equal to 1.22 lambda d. So theta resolution is the minimum value at which an object could be resolved, or the minimum angular distance at which two objects could be resolved. Notice that here from this Airy's disk setup, as theta goes to 0, for small angles, sine of theta is equal to theta. So these equations are very, very close. And then for small angles, here we're going to draw two separate objects. So here we're going to have a similar setup. Let's go ahead and draw our pinhole with a certain diameter d here. And then let's put a screen on this side. Here we go. Here's our screen. Now let's have two objects here shining light on through this hole. So let's have object 1. Let's draw it as a square. Here's object 1, here is object 2. So light coming from object 1, we already know how it's gonna, the type of image it's gonna form here on the screen. It's gonna be some blob like this. So let's go ahead and draw some light rays here. So we have light coming from this first object. We have a bunch of light rays coming from this first object, and then as they come through here, we're gonna get this like aperture diffraction pattern here, and the intensity here on the screen is gonna look something like this. And the same thing is gonna happen for this second object. This second object is also gonna be going through this slit here, and it's gonna form a similar pattern on the other side. So at this angle, these two objects are clearly distinct on the screen. We have two regions of intensity. However, as we bring these objects closer and closer together, so if we bring this object here closer to this one, as we reduce their angular distance, so notice that this angle here as it goes through the camera, or through the hole, as it goes through this hole here, these get closer and closer together. The projections on the screen. So this gets closer to this. And at that angle, theta res, you should be able to distinguish the two objects. However, if you go lower than theta res, what happens with the two images, they begin to overlap. So look, if we reposition these images like so, they begin to overlap, and beneath this angle, they just form one blob, and you can't distinguish between the two objects. So here, let's say that this is theta res, where we're still able to distinguish two distinct objects. We call that angle theta res. Any angle lower than that, and we can't resolve these two objects on this screen. So theta res depends on the wavelength of the light used. So that is the characteristic of the light that determines theta res, the wavelength. Theta res, that resolution limit, also depends on the diameter of that aperture. So that is the characteristic of the optical device that determines the resolution limit. A small resolution limit means that an angular separation that has a small quantity can be resolved on the screen. A smaller resolution limit is a more powerful camera that could distinguish, or microscope that could distinguish between two objects. So the lower the resolution limit, the better the microscope or the optical device that you're using here. The greater the resolution limit, so let's pretend the resolution limit for this optical device was way out here. If it was way out here, that means that the images that it's producing are gonna be much bigger, like so, such that if we get closer, we shouldn't be able to resolve these two. So they would have to be this big for the for these two intensities to interfere, and we wouldn't be able to resolve it. So we want a theta res that's smaller. The smaller the theta res, the more you'll be able to distinguish two objects that are angularly close together. So that is what is meant by that resolution limit given by this Rayleigh criterion equation.